Very happy to have Nikhil from Carnegie Mellon University. Nikhil is a PhD student with the Latencies group, and he's going to talk to us about functional fair exchange.
Yeah, thanks for the introduction and inviting me here to give a talk. Yeah, very pleased to be here. I'll be presenting two of my works on this topic, functional fair exchange, beyond all or nothing data exchange. And let me just start with a bit of background. So, not necessarily functional fair exchange, but where my background comes from and how it relates to this topic. So, okay, if we consider traditional digital systems, and suppose I'm messaging with Bhavis, okay, I want to give a talk here at 11, and he says, yes, okay, let's do that. And well, this is great, but if we want to keep this conversation confidential, then we can use public key encryption. As all of you might be aware, how this works. Like, I have a public key private key pair, Babis has public key private key pair as well. I encrypt using his public key, he can encrypt using mine, and so on. So this is the traditional way we can use encryption schemes to build secure communication systems. But modern digital systems are more complex. For instance, I can use a cloud service provider to store my, say, medical records on. And consider a scenario, okay, when I was coming to the US, got admission at Carnegie Mellon, and before traveling, CMU wanted to know, do I meet the vaccination requirements? And it can ask this cloud service provider based on my medical records, and the service provider can respond with this function output, whether it's true or false. So, well, this works, but as you can observe that these medical records are sensitive data, and I would like to keep them private. And by private, I mean I want to keep it hidden from the cloud as well as this organization CMU. And public key encryption doesn't fulfill all the requirements for meeting this. So what public key encryption allows is all or nothing access to encrypted data. So what this means is I can encrypt data, upload it on the cloud, but then there are only two things that can happen. If you have the decryption key, then you can decrypt. In that case, the cloud or CMU both will obtain the key and they can learn all of my medical records. But if I have this requirement that I only want them to learn this function evaluation, uh, that's something public key encryption doesn't enable. And there's this notion called functional encryption that has been studied in cryptography. And what this provides is a fine-grained way to access encrypted data and tries to address problems of this kind. In general, functional encryption provides a pathway that people need not choose between utility and privacy. And while functional encryption is a powerful cryptographic tool in this sense, there are many research challenges that show up relating to its expressivity, efficiency, security, and applications. And my focus has been making these tools expressive and efficient for real-world deployment. And broadly, I have looked at three domains of problems, which you can categorize in theory and applications. So on the theory side, access control is a classical problem in computer security, which has been very well studied. And it's a natural application of functional encryption. And I have tried to advance the theory of functional encryption on this side. I've also worked on anonymous communication, which is also a problem well studied in applied cryptography. And my work tries to bridge functional application with anonymous communication and show how it can be used, and also builds new theory for it. And the third domain that I'm specifically going to talk about today is we show new applications of functional encryption towards fair exchange. And in this line of work, we broaden the scope of fair exchange to something called functional fair exchange, as I will shortly talk about. And yeah, let's see what this problem is. So this talk is based on two works at CCS in Oakland, and these are works with my collaborators Garrett, Arvind, and Pratik. And yeah,
Sri is at University of Sydney.
yeah, he moved to University of Sydney, I think.
A professor.
Yeah, last year. Yeah, I think. Yeah. So, okay, let's start with what's the problem of fair exchange, and then we can try to understand what's this functional fair exchange, how it connects with functional encryption. So, fair exchange is a very simple problem. There's a buyer and a seller. The buyer has some money, the seller holds some data, and the problem we are trying to solve is the buyer is willing to pay some money to obtain this data in exchange. But crucially, both of these parties don't trust each other for executing the protocol and have some fairness requirements each. For the buyer, the fairness looks like if it sends the money, it should receive back the data it was expecting. And for the seller, the fairness requires that if this data is sent, then it should receive the payment. So both don't trust each other. If we just first say buyer sends the money, trusting that the seller will send back the data, but maybe the seller is malicious, right? So there could be challenges if you don't trust the other party. And as it turns out, Pagni and Gartner in 1989 showed that doing this fair exchange is impossible without a trusted third party. So, more recently, people have explored solving this problem using blockchains and the high level. Yeah.
You said the data the buyer was expecting.
Yeah.
The seller cannot just make up data, random data, and send it.
Okay. This is a little underspecified here, but we want the data that was promised. So
It's verifiable.
yeah. So I haven't specified that. Yeah. That will show up in the protocol description, but that's also a requirement. Yeah. So
I guess in the setup of this protocol, both buyer and seller see a commitment.
yeah. Yeah. So in the recent few years, people have explored how to use blockchains to address this problem. And a high level idea is that we want to use blockchain as a trusted third party to bypass this impossibility and get some feasible results for addressing this problem. And while we start using blockchains, there is another issue that shows up. So from a applied efficiency point of view, this is a additional infrastructure that we are using, and we would like to keep low on-chain costs and compatibility with various blockchains when we try to deploy these protocols. So these are also some things that we will try to keep in mind as we try to build these protocols. So what's functional fair exchange? The idea is that we want to generalize this problem with a functional encryption inspired notion, and I will explain why and where that could be meaningful. So now suppose the data that the seller holds is some sensitive information and it can't sell this data X as is, but it's say allowed to sell some function evaluations F. Okay, so the buyer will learn F of X. So similar to before, but just a little different. And the main difference now is that the seller has a privacy requirement that the buyer should learn nothing beyond F of X at the end of this protocol. And you may ask, why is this problem interesting? And let me give you two motivating applications. So first is consider some machine learning style application scenarios where, say, the sensitive data are some medical records and which are held by a hospital, and the function evaluation is, say, we are trying to fine tune a machine learning model on this data set, and the buyer is maybe a researcher or a big tech company who is trying to do this. So in this scenario, data privacy regulations such as HIPAA may prevent you from sharing all the medical records of the patients associated with the hospital, but it might still be permissible to allow function evaluations on this data. Maybe it's interesting for advancing medical research. Okay. So this is one style of applications where this data X is sensitive and we want this privacy requirement. The second style of applications you can think of are cryptographic applications. So think that X is a signing key. The seller is some certificate issuer. Buyer wants to obtain a certificate. And now this function evaluations essentially looks like a signature functionality. So buyer says, okay, sign this message for me, and the seller will issue a signature on that message. Okay. Again, in this scenario, the privacy requirements just comes from the cryptographic privacy scenario. So we can't just disclose the signing key as is, but it's fine to issue signatures. Okay. So these are the two high-level motivations of how this functional fair exchange could be an interesting problem to explore. And yeah, with that
Fair exchange, a protocol for fair exchange.
yes.
Can you build functional fair exchange by using generalized proofs?
Yes.
Okay,
It's
so
possible.
one way to do it.
Yes, it's possible. Yeah, I will come to that.
Alright.
That's the most natural way to do that. Yeah. Right. So, and I will highlight what are the trade-offs and how our work positions in contrast to those approaches. So let me quickly give a high level of how a fair exchange protocol could look like. I said that we can build protocols using blockchains. For illustration purposes, let's just use smart contracts. Okay. So the protocol could look as follows. At the beginning, say the seller has this data X, and what it does is encrypts it under a El-Gamal encryption scheme, sends this ciphertext as well as the public key to the buyer. This is the advertisement. So coming back to Aviv's question, so this is a kind of commitment that we are doing to this data. So we can't open to anything else. Okay. And simultaneously, then we can set up a smart contract where the public key, capital K, of the El-Gamal scheme is hard-coded. And the idea then is very simple and as follows. The buyer can lock in some money into the smart contract. After the seller observes that the money has been logged in, the seller can reveal this secret key, decryption key, little k, on chain. And the contract checks that this public key and secret key satisfy some relation. In case of El-Gamal scheme, it's a discrete log relation. If the relation verifies, then the contract releases the money to the seller. And since the key little k has been published on chain, anyone can observe this, including the buyer, and it can decrypt the ciphertext to obtain little x, which is the message. So in a sense, the smart contract is enabling this fairness. The logic is baked into the smart contract that if the verification passes, then release the money. And simultaneously, anyone can do this. Does this make sense? Yeah.
If you want just the buyer to find out this data and you don't want other parties that can.
Right. So
see
in the
shit?
first step, this could be sent privately to the buyer.
Oh, okay.
Yeah. So while the key little k is public, but the ciphertext is only privately known to the buyer. So that should ensure only the buyer learns little x. Yeah.
So this protocol is not really helping, I mean, it's not protecting against abuse attack where the seller can send some garbage as X.
Yeah. So there is one part missing over here. I wanted to keep it simple, but you can say that in addition to the ciphertext, you can, at the time of generating the advertisement, you can give out a ZK proof attesting that,
Satisfied.
yeah, like there is some public information about this little x,
Right.
and you're saying that it is the witness to that.
I think you probably also need the provenance proof for X, showing its source came from a particular website or something.
So, what exactly is the provenance proof?
For example, you're showing X is indeed from a medical record, not
Yeah,
from
yeah.
a utility.
Yeah, yeah,
company or-
yeah, that's right. Yeah. So, yeah, that's also there. It depends on
Also-
as part of advertisement, how do you model that? For the purpose of this talk, our focus is not going to be on this ZK proof for the advertisement. The focus is going to be more on what happens after generating a well-formed advertisement. Yeah. So, okay, given this smart contract based protocol, a natural idea to build functional fair exchange now is as follows. So instead of using this El-Gamal public key encryption scheme, I'm going to replace it with a functional encryption scheme. I haven't introduced what's the syntax, but it will become clear with this protocol. The idea is that, okay, in first step, instead of the El-Gamal, I will use a functional encryption, encrypt the ciphertext using it. And after that, second step stays same as before. In the third step, things are a little different now. Instead of just publishing a decryption key on chain, what we are going to do is compute a function specific decryption key denoted dk sub f, and now publish this on chain. And the idea is that the way functional encryption works is as follows. Given a function specific decryption key, if you try to decrypt the ciphertext, you won't learn X, but you will only learn f of X. That's the functional encryption syntax on a high level. And it gives security to this end. So if we can do this, then I'm just making two small modifications. One, instead of El-Gamal, I have replaced with the functional encryption scheme. And second, in the smart contract, this verification is replaced with a little different algebraic structure. So we are verifying that DKF satisfies some relation with respect to the encryption key and some function description F. Okay. And on a high level, what's happening over here is the smart contract is enabling an atomic swap of money and this functional decryption key DKF. Okay. And this is the baseline I want to start with. And we will build on top from here because, okay, there are two main downsides of using smart contracts. One is that it results in high on-chain costs. And second is smart contracts are incompatible with blockchains such as Bitcoin. And we can ask this question, can we build similar protocols without using a smart contract, just use a bare minimum blockchain functionality? Okay. So the key challenge we try to address in our works is, can we design functional fair exchange protocols without using smart contracts? Yeah.
Just a quick one. So the high on-chain cost on smart contracts, is that primarily because the relation that you said the smart contract has to verify? Is that not efficient?
Yes. So depending on the complexity of this function f, this relation may not be efficient to verify.
Depends on the function.
Yeah.
So this incompatibility part, it can that be maybe partially mitigated with the wrapped Bitcoin on a Ethereum, smart contract chain?
I haven't closely thought about that, but as I understand, wrapped Bitcoin also introduces more trust assumptions of how you're wrapping things. So
There are different ways to wrap them, but I mean, So, and that's potentially one, like the way to also mitigate the content.
Could be. I guess the main trade-off then would be this trusted third party. How much trust are you putting in that? Like, say on an Ethereum blockchain, we are not trusting one single party. It's like the whole blockchain and whatever trust assumption Ethereum comes with, say 2/3 majority or something. In the wrapped settings, I don't think that is the case. So I think that mainly the trust assumption will change.
There are different ways to.
Okay, yeah.
Potentially additional trust, but
Yeah.
whether it's palatable or not, I think.
Yeah, so I think it should be feasible. That I just wanted to highlight that this might be the trade-off you're making. So more trust assumption and the protocol description becomes simpler. Yeah. And yeah. Yeah, so as I said, the key challenge we try to address in our works is, can we avoid using smart contracts to build functional fair exchange protocols? And our contributions in these two works are as follows. So in the first work, we show how to do functional fair exchange via adapter signatures and functional encryption. So mainly we replace smart contracts with adapter signatures, and that's what I'm going to talk about. And the second line of work, so the first line, while we can use functional encryption and instead of smart contracts, we are using adapters. But these two primitives are a little difficult to play along with, and there are some compatibility requirements which restricts to only supporting linear functions, even with using functional encryption. Yeah.
So I have a question. So when you say like avoid smart contracts, are you avoiding the blockchain setting or? Right, but what does it mean to avoid smart contracts?
Yeah.
You're avoiding like a distributed system, implementation of the trust using a distributed system that runs with consensus, or you use adapter signatures with a single trusted party. So I don't.
So more to do with the former. So think like, okay, the smart contract based solution, I can't directly deploy using Bitcoin blockchain.
Right. So you want to use adapter signatures on a Bitcoin setting.
Yes.
So you're still gonna use the blockchain.
Yeah,
just
I am
like
still going to use the
implementation,
blockchain. Yeah.
And you're gonna use the Bitcoin blockchain.
Yeah.
Okay.
That's right.
And right. Okay. Okay.
Yeah. So the first solution I'm going to present is going to be using adapter signatures and functional encryption, but it's going to be restricted to only supporting linear function evaluations. And in the second work that's going to appear at Oakland, we show how to replace functional encryption with fully homomorphic encryption. And then our protocol can support arbitrary function evaluations. So the high level idea of the first line of work, just a single slide summary, is as follows. So previously we were doing this atomic swap of money and this functional decryption key using a smart contract. What we are going to do is now we will enable the same atomic swap, but instead we will enable it using an adapter signature. And a consequence of doing so is that only a single signature will be posted on chain. So not only it avoids using smart contract, it also reduces the on-chain cost to be the bare minimum that's possible. Just a single signature goes on chain, which you can think is going to be required since a payment needs to happen. Yeah.
Right. So the blockchain is used only for this payment.
Yes.
Okay. And is this somehow the trusted party that you need for the invoice?
Yeah.
So why can't I just pay in a different way? Like I give you, say the output is instead of a signature, I don't know, a signature to my bank account or something, like which lets you take the money from there. So then why do I need
So that's another trust assumption we are
What is it
involved, like
assumption
the signature, when you go to the bank will transfer the money. So yeah. And a single slide summary of how the FHE style protocol would look like is it will be slightly different. Instead of functional encryption in step 1, I will use fully homomorphic encryption. And okay, what happens, what's the upside of using FHE is that the buyer can just do a FHE evaluation on the original ciphertext and obtain encryption of f of x. And beyond this, well, okay, you can think, okay, now you have CT sub f, then if I can obtain the decryption key, then I can learn f of x. But the downside of FHE is if I give away the decryption key, you can also learn x as is. So how do I ensure using FHE still revealing only f of x? A natural idea is that the seller can just decrypt the FHE ciphertext on its own and re-encrypt using a different scheme, say El-Gamal encryption, this f of x value. And then it requires some additional proofs, but the idea is that if I send over El-Gamal encryption of f of x, then if I just do an atomic swap of the El-Gamal key, then f of x can be learned. That's the high level of how things are going to be. There are many details I'm sliding under the rug here, and we will get to it. And just to give a high level comparison of all these protocols, so the smart contract based approach can support arbitrary functions, but the downside is the infrastructure costs and the infrastructure incompatibility. On the other hand, if you start using adapter signatures, just using public key encryption, you can support identity functions. Using functional encryption in our work, we show that you can do linear functions, and the FHE approach allows to support arbitrary functions. In all of these protocols, the infrastructure costs are bare minimum, and the compatibility holds with blockchains such as Bitcoin. Yeah.
This code refers to Bitcoin implementation,
Yes.
and the reason the infrastructure costs are not significant.
Just single signature on chain.
So you're not running any complex smart contract
Yeah.
code, but you could potentially use smart contract to still do one signature, right? Just trying to understand what's the. I mean, my point is that you could take your system and implement it on Ethereum.
Yes,
smart
yes.
contract, right?
Of course.
So
In that sense, okay, still the on-chain cost, like whatever gas cost that you are getting on-chain, will be bare minimum on the Ethereum blockchain as well.
right.
So yeah, in that sense, it's a efficiency improvement.
It is a better way to implement the system using a smart contract by using this adapter signature
Yes.
as opposed to
Yeah. You can
just
think.
using a functional encryption straight up.
Yeah. So you can think this is a layer 2 solution with minimal on-chain costs in that sense. Yeah.
Another related question. So if we relax the compatibility requirement.
Yeah.
Is making the efficiency, it is making it more efficient and reducing the cost.
Yeah.
Still as challenging or
So okay, then the difference is the following. You can say, okay, forget about this infrastructure. I want to stay on Ethereum blockchain and say I want to use a standard ZKVM EVM style L2 solution. The difference would be on chain, there will be a proof that's published with a ZK EVM approach, which you need to verify, versus in this case, it will be a signature. So there are still going to be efficiency benefits verifying a proof versus verifying a signature. Signature verification is likely going to be more efficient.
right, the ZKVM is the straight, like is the baseline.
Yeah.
But do you think if we don't have this compatibility requirement from the get-go and we just want to be more efficient at DKVM,
Yeah.
is there a simpler solution or it has to go to the adapter signature as well?
Yeah, so even doing better than ZKVMs, I think yeah, adapter is one solution. Is there a better solution? I don't think so. Like, yeah, like on-chain, a single signature is bare minimum. Yeah. Yeah.
Two questions for the adapter plus PKE. Why not just encrypt f of x?
Yeah, I'm coming to that. Yeah.
And for the second, for adapter plus FE,
Mhm.
why only linear?
Right. So to answer the first, if you just encrypt f of x and just give a ZK proof, the main difference is this ZK prover's complexity depends on the function description f.
Oh, the
So
point was that
it's possible to do that.
you
Yes.
need to prove that f was
Yeah, yeah.
right to x. Okay.
Yeah.
Okay, that's-
So the trade-offs are the protocol you're trying to build. Is that like buyer efficient, seller efficient, or overall most efficient? Yeah, those are the trade-offs. For second, this linearity, I can't directly answer right now. Once we see the protocols, it will become evident. But it has to do with some algebraic structural requirement between adapter signature and functional encryption.
Or in the sense, like, what you're showing is it's impossible to do anything else besides linear. It's not that you just can show linear.
I wouldn't say it's impossible. It's more to do with adapter signatures. What are they known for? Like the feasibility of adapters and feasibility of functional encryption. It might be possible in future, but the schemes that we know of today, I think we can only do linear. Yeah. Other questions? Okay. Right. So the plan for rest of the talk is as follows. We will start as a warm-up with, I will introduce what are adapter signatures and how they can be used to build a simple fair exchange protocol. Then second, we are going to see how to build functional fair exchange using functional encryption along with adapters. Third, we will look at how we replace FE with FHE. And lastly, I will briefly talk about our implementation and performance. So far things have been quite informal. Let me try to formalize a bit. What's a fair exchange protocol? So we follow the definitions of this recent work from 2025, and on a very high level, there are three things that happen. At the beginning, there's a setup algorithm which generates some public parameters. Then the seller who holds little x as its private input can generate an advertisement, send it to the buyer. And after this, the third stage is the exchange phase. It's an interactive protocol between the buyer, seller, and a trusted third party, at the end of which the buyer's output is beta, the seller's output is alpha. For visual simplicity, I haven't denoted the trusted third party here, but in the protocol descriptions, I will highlight it wherever it shows up. And with this protocol, the requirements are as follows. So correctness requires that if everyone behaves honestly, then the output beta at the end should be the value X. The output alpha should be the bitcoins held by the buyer, so they get transferred to the seller. Buyer fairness requires that the probability of this bad event from buyer's point of view should be negligible. So what we are trying to ensure, recall that buyer wants to ensure if it sends the money, then it should receive the data. So the bad event is if it sent the money, so the Bitcoin is not held by the buyer anymore, and the data obtained is not what it expects. This is the bad event. The probability of this bad event should be negligible. Seller fairness requires that if the seller did not obtain the payment, then the buyer should learn no information about its data. And it's captured through a real and ideal world paradigm. And we consider real and ideal worlds, in both of which the alpha part is bought output, meaning it did not receive any payment. And in this case, what we essentially try to capture is that the buyer learns no information. This will be captured in the ideal world through a simulator that does not get little x as input. If the buyer's view is indistinguishable in both these worlds, this essentially will capture the idea that the buyer learns no information about little x. Sounds reasonable? Okay. So that's the definition for fair exchange. Now let me introduce what adapter signatures are, and it might be helpful to think of those in the context of fair exchange, since they naturally induce a fair exchange protocol itself. So I have drawn that protocol on the right. But what are adapter signatures as a standalone object? It's a signature scheme defined with respect to two things: a digital signature scheme and a hard relation R. And it specifically consists of 4 algorithms: pre-sign, pre-verify, adapt, and extract. These algorithms have the following properties, and the way I want you to think of them is in the sense of this fair exchange protocol. So what's happening? In the fair exchange protocol, the buyer has some bitcoins and a secret key. The sellers has data little x, which is secret, and capital X is a statement, which is like a commitment. Imagine capital X is like a commitment to this data little x. They satisfy some hard relation R. So the seller sends capital X to the buyer. This is like an advertisement. Then the buyer issues a pre-signature. And this pre-signature is generated on this transaction to transfer the bitcoins, but also with respect to the statement capital X. So it's tied to the statement capital X, okay? And the nice feature of this is that if the pre-signature verifies with respect to statement capital X, then the seller can run an adapt algorithm on the pre-signature to compute a full signature. Note that both the pre-signatures and the full signature are with respect to the secret signing key SK of the buyer. So at this stage, the seller is computing a full signature under the key of the buyer, and it can publish this transaction along with the signature on chain. And correctness essentially requires that if you do so, if you adapt a pre-signature into full signature, then the signature verification should pass, meaning that the transaction gets accepted on the blockchain and you get the payment. So the seller publishes transaction on chain and gets the payment. Okay. Lastly, there is this extract algorithm. What is it doing? It says that given a pre-signature and a full signature as input, you can extract the underlying secret little x. So note that the pre-signature was tied to this commitment on little x. And then we used this little x to adapt into a full signature.
Extract an efficient algorithm.
Yes, it's an efficient algorithm.
And anybody can run.
If anyone who has pre-signature and full signature can run it, yes. So while these 4 algorithms might seem little strange, I think it helps to understand them in this context of a fair exchange of what's happening. So the fairness comes from the fact that as soon as the seller publishes signature on chain, the buyer can extract and the seller has obtained the payment. So one task triggers 2 events simultaneously. And in terms of security, there are 3 properties, 2 of which are defined with respect to a malicious seller, which is, the first is unforgeability, which essentially says that it's similar to standard unforgeability definition, but it should also hold in presence of pre-signatures obtained by an adversary. So even if you have Oracle access to obtaining pre-signatures, you should still not be able to generate new signatures on your own. And witness extractability is a little complex, but in essence, both of these properties, when you try to look at them in a combined way, they try to ensure buyer fairness of this induced protocol. So what's buyer fairness? If the bitcoins are transferred and beta is not equal to x, this event should be with negligible probability. So unforgeability says that the possibility that bitcoins get transferred without the buyer doing anything is negligible on its own. It only talks about generating new signatures unrelated to things for which you obtain pre-signatures. Witness extractability essentially captures the second part. Okay, if I issued pre-signatures, honest buyer issued pre-signatures, and okay, a seller can naturally just adapt and obtain the payment, in which case the bitcoins are not held by the buyer anymore. But when this event occurs, the probability that the extract algorithm fails essentially is negligible. That's what witness extractability captures. And the the third property is against the malicious buyer. It's called pre-signature adaptability. All it says is, okay, if there is a malicious buyer who issued some pre-signature, we don't know how it was computed, but as long as it passes the pre-verification, then an adapted pre-signature should always verify. And this also naturally results in the seller fairness. And how this works is as follows. So recall what was seller fairness. We want to say, I want to build a simulator instead of a seller. And the simulator never gets little excess input. And how could this simulator look like? It looks as follows. So we are only interested in scenarios where alpha is equal to bot. In this protocol, observe that if the pre-verification passes, then this property says that adapt should go through. If the adapt goes through, the output alpha is never bought. So all this is saying is alpha equal to bot essentially means that pre-verification did not pass. If pre-verification did not pass, then I never need to adapt. The seller never needs to adapt. And recall that in this protocol, seller needed little x only for the adapt stage. So what's the simulator look like? The simulator only gets the statement as input. It just runs the first step, sends it to the buyer pre-signs, pre-verification fails, and the simulation ends then. So that's a very high level of how adapter signatures ensure these two fairness requirements. Okay. So, right. So, as I said, this is for a fair exchange for a very specific witness little x, which satisfies some discrete log relation. If we want to generalize this, we can use public key encryption. So if there is some data little x, I can just encrypt it using a public key encryption scheme. And beyond this, just use the adapter signature to do atomic swap of money and the decryption key. So this generalizes from fair exchange for this specific seller witness to any witness that you may want. And how this could look like, essentially, you pre-sign with respect to the encryption key and adapt using the decryption key. This essentially means that this encryption key, decryption key satisfy this relation R, and I'm using adapter signatures for this specific relation R. And yeah, once you extract the decryption key, you can decrypt. And what's the example instantiation? We know adapter signatures for the discrete log relation, which are essentially the Schnorr adapter signatures. And the El-Gamal encryption scheme satisfies the discrete log structure between the encryption and the decryption key. So we can use this as a stepping stone to build fair exchange for any data little x of interest. Yeah. Does this make sense? Okay. So the fairness properties follow very similar to before. Buyer fairness is exactly same as what I said. Seller fairness just requires one more step. Since I'm using encryption scheme, and in this protocol, seller fairness talks about scenario when the seller never gets a payment. So the seller never needs to reveal its secret, which is the decryption key. If we never need to reveal the decryption key, then I can simply use the semantic security of PK to switch the ciphertext in the first step to an encryption of 0, and simulation goes through with that. So yeah, now that we have a protocol using adapter signatures, let me come to this strawman protocol idea. This goes back to the high level idea that Babis was suggesting earlier. If I want to do functional fair exchange, what I can do is simply the following. Okay, I start with public key encryption as before, and next the buyer sends the function. And what I can do is set up a different instance, like the seller knows f of x at this point of time, and do a fair exchange of f of x, right? And we are kind of done. So if I generate a new instance of Elgamal encryption, and if I give a valid proof that CT prime encrypts f of x, and the origin where x is encrypted under CT in the first step, then this shows a way to use simply a fair exchange protocol to do functional fair exchange.
So this requires adapter signatures here?
Yes. So essentially, the second instance has little k that I'm trying to do atomic swap for. So you can use smart contracts or adapters for this. So this part is changeable to smart contracts as before, but essentially it captures the idea that you were suggesting, that you can do a Nizic proof and this should solve the problem, right? The main issue is that this makes the seller inefficient, as I was alluding to earlier. Specifically, the cryptographic operations involved here depend on the complexity of this function f. And if you recall, I gave two high-level applications. If you think about this fine-tuning machine learning model, there's a buyer who is a researcher or a big tech company who wants to fine-tune a model. The seller is a hospital, and there's a natural asymmetry. Buyer has more compute resources than the seller. So asking the seller to do this function-dependent computations, not only in plain, but also doing cryptographic operations, is a little asymmetric. And you can ask this question, can I design a protocol that is seller optimized?
So the complexity of F in any protocol needs to show up somewhere, right?
Yeah, it needs to show up somewhere. So
your approach, where does it show up?
So in our approach, it will show up on the buyer side. So like cryptographic operations that depend on F, that will only show up on the buyer side.
And this is better for applications.
Yeah, so it's like a better fit for these style of applications. So you can do this, but the protocol from this will be buyer efficient, not seller efficient. If buyer has more compute resources, then you can try to build like maybe protocols which are optimized for the seller, not necessarily for the buyer. And that is the regime where our solutions lie in. And yeah, so
in the seller inefficient approach, the inefficiency comes from the fact that you have to compute the zero knowledge proof on the circuit that does the ML computation. Every time you have an X. Like, so every time you run a protocol, you have to compute that, right?
Yeah.
And in the other approach, you do have to compute at the buyer.
Yes.
Every time again.
Yes.
There's no notion of like one time setup.
We haven't considered that, but that could be an interesting question as well. Like if the same function f is being repeated on different inputs, can you do that? So yeah, let me dive into how our protocols look like. And before that, maybe just a very quick note on what's the definition of functional fair exchange. It's similar to before, but there are few things that are different. In correctness, we require this output beta of the buyer at the end of the protocol is supposed to be f of x. Buyer fairness is essentially same as before, just beta not equal to x is replaced with beta not equal to f of x. Seller fairness is also same as before, but there is also seller privacy requirement that I suggested earlier. The privacy requirement is also going to be captured through this real ideal world, where we say there are two different scenarios here. Fairness asks about what happens when the seller output alpha is bought. In this case, the simulator does not get X as input as before. The privacy says that, okay, when the seller does get a payment, what happens? What does the buyer learn? And we say that the buyer learns f of x. We will capture this through a simulator that only gets f of x as input. It does not get x as input. So the definition style is going to be same. Just the difference is for privacy, we will allow the simulator to get f of x. So how does our protocol look like? It will be based on functional encryption, as I said earlier. And to understand the protocol a little more intuitively, I will introduce a public keygen algorithm, which is similar to this keygen algorithm, but it runs on the public key. So keygen takes the decryption key and a function and outputs a functional decryption key. This algorithm outputs a functional public key. So it's like a sister algorithm to the keygen, but on the public parts instead of the private. This is a deterministic algorithm, and it won't affect the correctness or security of FE, but it helps to build intuition. And a new property that we will require is something called R compliance. So we say that a FE scheme is R compliant if this EK sub f and DK sub f satisfy some hard relation R. And it's going to be useful as follows. So recall what was the high level idea. The high level idea was we will do atomic swap of money and this functional decryption key, but now using adapter signatures. And this looks as follows. So the buyer is going to set up a pre-signature with respect to EK sub f. So EK sub f acts as the statement. And after this, the seller adapts using DK sub f, the pre-signature, into a full signature. If this goes through, then the buyer should be able to extract the witness, which is DK sub f, from this adapter signature. So essentially, just everything is same as before. I've just replaced what's the statement and the witness. Instead of El-Gamal keys, the statement is EK sub f and witness is DK sub f. And this is where the linear restriction shows up. The main challenge is what's this? We need to ensure compatibility of the functional encryption and the adapter signatures. Specifically, if the adapter is defined with respect to a hard relation R, then the FE scheme needs to be R compliant. And next, we also need to choose adapters that are used on blockchains. And our solution is, okay, let's go back to the Schnorr adapters, which are for the discrete log relation. And we observe that this FE scheme for linear functions by Abdullah et al. From 2015, this can be augmented with a public keygen algorithm to make it R compliant. And by instantiating with these two building blocks, we can get a theorem statement of the following kind. So buyer fairness more or less stays the same as before. For seller fairness, instead of IND security of EK, we can replace it with functional encryption. And for seller privacy as well, it follows from roughly the same two properties. I won't have the time to go into those details, but yeah, That's the high level idea. These two instantiations restrict with this linear functions. And the second challenge then shows, then, okay, as it turns out, we don't know of any FE schemes beyond linear functions that are compliant. So we don't say that it's impossible, just the adapter signatures that we know of and the FE schemes that we know of, we don't know beyond this. And our key idea then is going to, if we want to go beyond linear functions, we can try to use FHE. And that's what I will briefly talk about. So how does the FHE protocol work? To recall, there's a FHE encryption, the buyer does the FHE evaluation, and now the seller does FHE decryption, generates a Elgamal instance, and generates a proof that CTF and CT prime F encrypt these same values. And once we have a proof and send over the ciphertext with respect to key capital K, then the idea is same as before. We just need to do an atomic swap. And there's nothing new over here. The key novelty lies in generating this proof pi. So if you recall, what was the strawman? Strawman solution was doing a Nizic proof itself, but that was a computation that depends on F. And now you can ask, okay, you're again doing a Nizic proof, what's the upside? The upside is this proof is going to be much more efficient. So essentially it's a cut and choose style Sigma protocol. I won't go into the details, but the idea is that this proof takes witness Z, R prime, and okay, this should be R sub Z, where how do you compute the Nizic witness makes things efficient or inefficient. A naive way to do this witness computation would be like invoke a sister algorithm for FHE evaluation, which instead of doing FHE evaluation on the message, it does it on the random coins of the ciphertext. And essentially what we want is, we want to generate the random coins R sub Z such that the CTF is an encryption of Z under these specific random coins. The naive way to compute this would be through the sister algorithm, and this sister algorithm would be inefficient. It depends on F. But our key observation here is we can optimize this as follows. So if we look at the FHE schemes under the hood, they have a key switch and a bootstrap algorithm. And we crucially rely on the key switch algorithm over there. Essentially, all it says is that if I try to apply this key switch algorithm, I get a fresh encryption of the same message under a different key and a different random coins. Okay, different random coins, but these random coins are very easy to compute. I don't need to go through the full F evaluation. I can just evaluate these random coins as an inner product of the random coins of this underlying key and the ciphertext that you have homomorphically evaluated. So that's the main observation that makes our protocols efficient. This R sub Z is essentially just a linear computation. This linear computation only depends on the output length of F. So like output length of F determines the output length of CT sub F, and then just an inner product on that. And yeah, this makes it essentially constant time computation. And just quickly about the implementation and performance for linear functions and for FHE, I just highlight performance numbers over here. And this compares the FHE with the snark-based approach. The solid lines are for FHE scheme, the dotted lines are for the snark scheme. And the key trade-off that our scheme obtains is these black lines for the FHE seller and the dotted black line for the snark seller. Our FHE seller is this flat line, which is a constant time seller algorithm. And this dotted line is for the snark-based seller. It scales with the complexity of the function f. On the other hand, there is one downside. If you look at the total time, which is the orange, the total time of our protocol is worse compared to a snark-based scheme. And that is mainly because of the efficiency of a FHE scheme versus efficiency of a ZK snark scheme. As we know today, snarks are much faster than FHE. So in overall time, our protocol is not faster, but our protocol is faster if you are really concerned about making a seller efficient. And yeah, that concludes my talk. Yeah, I talked about functional fair exchange, showed how to build it via adapters, and then how to replace PKE with functional encryption and FHE. Yeah, there are a bunch of things that I did not have a chance to talk about in the paper. And yeah, there are a bunch of open questions that are exciting, and I will leave you with those. So there are some communication computation trade-offs. You can explore like how many rounds of interaction happen between buyer and seller. Then you can ask the same fair exchange protocol, but generalized to a multi-seller scenario. It could be interesting from practical point of view. You can also consider dual notion where the seller holds a function description and buyer holds some data X. And yeah, more broadly, okay, we show how to enable this fair exchange application on Bitcoin. You can also ask, can you do more use cases on Bitcoin? And yeah, with those, I will, yeah. Thank you for attending the talk.